Hey everyone, welcome back to my fifth part of deep neural networks for image classification with numpy. So in this tutorial we will use the functions we had implemented in our previous parts to build a deep network, and we'll apply it to cat versus dogs classification. So hopefully we will see an improvement. Well, at least we should see an improvement in accuracy relative to our previous logistic regression implementation. And after this part, we'll be able to build and apply a deep neural network to supervised learning using only a numpy library. So let's first import all the packages that we will need during this part. So we'll use the same cat versus dog dataset in the logistic regression as neural network we used. So before, the model we had built had 60% test accuracy on classifying the dogs versus cats, and hopefully our new model will perform better. So what I'll do is, this is the code from my last tutorial, so I'll just remove few lines here and I'll just import what we are necessary to do further. So I'll import all the imports we'll need, add here, and of course I'll add the code we had before. So here is my code from logistic regression tutorial. This is the code for my dataset preparation. So here we are reading images and here we are preparing them and we are placing them into a shape we need. So in this tutorial, it is hard to represent a deep neural network with figure. However, here is a simplified network representation. So here is our deep neural network. So the input is the image with 64 pixel size of 3 layers. So it's RGB image, and there it goes to linear unit and ReLU unit, and here is the for loop, and it depends on how deep our network is. So for example, if we have our 3 hidden layers, this loop will go 3 times and so on. And here is our last layer. This is a sigmoid, and yeah, that's it. And then we predict this as a cat or a dog. So if the sigmoid unit gives us probability more than 0.5, so it means this is a cat, elsewise it will be a dog. So what is the general methodology? So as before, if you watch my previous tutorials, you already know that first we initialize the parameters and define hyperparameters. Then we loop the for number of iterations. So we are doing forward propagation, we compute the cost, we doing backward propagation and updating the parameters. We are doing this loop, I don't know, many times. And then we use trained parameters to predict it's a dog or a cat. That's simple. So I'm not getting into a theoretical side as before. I'll just begin of modeling. So before we made all the models and functions which we need to write actual model, so here I'll just start building this, and this should be quite easy. And okay, I'll define a new model, so it will call L layer model, and here will be all inputs. So it will be X, Y, layer dimensions, we'll call layer dims. Next will be our learning rate, which default gonna be 0.075. oh sorry, bad, this one 75 to 0, sorry. Number of iterations will be equal to 3000, and we'll write a print cost by default gonna be false. Yeah, that's it. That will be our inputs, and here we'll just write costs will be equal something. Here will be our costs list. So at first we initialize our parameters. Initialize parameters deep, I think, and here will be my layer dimensions. So here will be my loop for I in range, and here will be from 0 to number of iterations, just like that. Sorry, this is not the way it should be. This is, and here we first do for propagation. So AL will be, and caches will be equal to L model forward. L model forward, and here will be my X and parameters, just like that. Then we go with cost, and cost will gonna be a compute cost AL and Y. Then we go with gradients, and here we do our backward propagation, and we call it L model backward. And here goes my output from our for propagation. Then goes our actual labels, and here goes our caches. And next we do is, well, we just need to update parameters. Update parameters, and here I'll write parameters, grads, and learning rate, of course. What learning rate we will use to update our parameters. And here we actually finished our model. So here is just for ourselves now code. So I'll use it for printing the cost. So if print cost and I divided by 100 is equal to 0, we print the cost after iteration I will be equal to F, just like that. And what else is, yeah, we'll add here our I and the cost. So we'll print this. Here will be I, and here will be our F, and one more function. If print cost sorry, and I divided by 100 is equal to 0, we'll use costs append our cost. So that's, we simply add this to our list of costs. So we finished our training loop. Here we just now write a plot function that when we train our model, so we could see what was our training cost function, how it looked, and that's it. So we use a PLT, matplotlib we use, and here I'll just write a plot numpy squeeze. We'll reduce this and costs. plt.ylabel label will be equal to cost, or pltxlabel will be equal to iterations per tens, just like that. And plt title will be our learning rate equal to something. So, and our something will be just a learning rate. and last is plot show, and here return parameters. Just like that, we have our function here. This is our training function, and we will use parameters to, of course, predict. So one more function we'll need is predict. I just mentioned it, so I define a predict function, and inputs will be x, y, and parameters, just like that. And I'll try to be fast. And now we need to get a number of examples shape of 1, and this way we'll take how deep our network is, length of parameters, and divided by 2. We take this will be our predictions, and this is numpy zeros of 1 and m, prob and caches we need also from our for propagation. So I'll just add modal forward because we use it to predict, and here will be our x and parameters. And after this we have our predictions as here. So for I in range of from 0 to probabilities as shape of 1, we do something like that, is prob as, and here it will be from 0 to I. Oh, this is, it should be 0. If it is more than 0.5, our predictions will be 1, so will be 1, and else it will be predictions of 0, y, and equal to, just like that. And we return our prediction. Sorry, I'll try to be fast, not to take this tutorial too long, because it might be too long. And now, as I have imported our preparation of data and so on, where I have it, let me check it out. Here it is, everything I need. And now what else I would need is I need to write a prediction. So actually what I should do, I should write layer dims that my input will be 12288 800 10 and 1. This is actually the input of our images. This is our first hidden layer, second hidden layer, and output of sigmoid. So 4 layers network. And if we would like to write parameters, if we would like to write train our model, we do model layer model, and here we would do train set x, train set y, and here I would use layer dimensions. We would use learning rate of something like 0.1. You should test it by yourself. Number of iterations would be, I don't know, we would need, for example, 10,000, but it would take very long with our images, but this is the cost of our neural networks, and our print cost would be true, I think. This would be the way we would like to train our model, and then we would use a predict function. So what would be our print function doesn't matter right now, because I think I won't try to do this right now because it might take too long for you, but I will do this later. I will leave it for night because it on CPU might take very long. So I don't know, one night or maybe longer. So elsewise, what I will do is I'll try it on something different, so smaller data set or whatever you want, and I'll just import a data set I had written in my page. So I'll just copy it and paste, so I won't waste your and mine time. And this is simply a load data set and plot the decision boundary. So this will be a function to generate a data set, and this will be used to plot our predictions. So anyway, I'll comment these lines, few lines, so this won't disturb us because it takes long to load the data set and so on. But as I said, we'll try something different. So at first, let's try it and let's simply plot it. Train Y, test X, and test Y. And here will be my load data set. And here I'll use data noise of 0.15. Then I'll use visualize as true. So I'll just write a true. So let's try it, build, and oh, sklearn is not imported. So okay, let's go to the top and import it. sklearn, I'll build this. Okay, from sklearn import data sets. I think this should work. Okay, as you can see, there is our data we'll use as neural networks, and as you can see, here is our two squares going round. So if I'll remove our noise, it would be much easier to see what it actually is. So I can write something like 0.1. Let's build this and you'll see. As you can see, this is what it is, but noises makes it difficult. So it's easy to see where is the border of one and another, but we'll use 0.15, so it's much harder for our network. So as we already have imported and shown what is the data set, now it's time to train it. So I'll write a false. I don't want to see it anymore in our later functions. So what I'll do here is I'll just, where's my above function? I'll just copy this and paste here, and I'll use our input will be 2, here is 4, and I'll use here train X, then train Y, learning rate will be 0.2, number of iterations will use as 50,000, and of course, yeah, we can print the cost as true. And one more line, what I'll need is the accuracy, I think, sorry. So here we have our model training, and what we need to print our accuracy. So what I would use is train, and here will be train accuracy of something in here, and now it will be as format 100 minus numpy mean of numpy apps and here is predict function of train x and our trained parameters. And here we minus train y, and here we multiply it by 100. So this way it will print us the accuracy. And now we use plot decision boundary, and here we use this kind of function lambda as x of predict of our x transposed and parameters, trained parameters, and here we use train of x and train of y, just like that. And yeah, I think that's it. We can check it out. What is the accuracy? Okay, let's pull this. It's training, as you can see. It might take 50,000 steps. Okay, where's the problem? Cost. Train X, train Y, layer dims, learning rate, number of iterations, print cost, true. Okay, give me a moment here to fix this. I'll write here a string maybe. Not sure what's wrong here, but I might try this. Oh, here's the... No, not a problem here. Well, cost and numpy squeeze costs. Well, anyway, it should be fine now. Let's see. X label. Yeah, it's fine now, as you can see. And here's our plot, as you can see. Here was the training, how it looked like. And as you can see, it's here started to decrease. And let's see what is... Okay, one more error. Okay. Parameters. What's... What's wrong here? Train X and parameters. Where's our predict function? Oh, yeah. Here. We don't need this I. Why? Okay. My mistake. Sorry. Let's build one more time so there won't be any mistakes anymore. Just like that. As before, it's quite similar, not the same because we are using random. Okay. Zeros, no attribute of zeros. Okay, that's my another mistake in predict functions. Let's go further. Okay, again, quite similar but not the same. And as you can see, our accuracy is 73, and it has some kind of predictions, but as you can see, the corners are quite sharp. So, well, not that fine. So we can train another model. Let's test, for example, this was quite similar to our neural networks with one hidden layer, with 4 layers in hidden. So let's try it with 10th, and let's see how it will look like. And there should be a little more accuracy, as I think. Here it is. It's trained and accuracy of 77. It's quite nice. It's more than 73 as it was before, but this also depends on random numbers. So everything looks fine. Okay, and now let's try our deep neural networks. And for example, let's try with 128 layers, and here let's try 4. It might be lower than 77, I think, but we'll see. Okay, as you can see, it's going slower, so I'll make it skip this. So as you can see, here is our training cost, and as you can see, after half of iterations is just dropped sharply here. And this is the structure how we developed our deep neural networks, because we have here a simplest neural network as we can have. And let's see what we have. The training accuracy, oh damn, it's 80%, and damnly it drew a very nice the bounding box, and as you can see, it's quite nice. And what I should say that congrats you. It seems that our deep layer neural network has better performance than our one hidden layer neural network. And maybe I'll upload this to my website, and then I might receive a different results. But as you can hear right now, our deep neural network has better results. So on the same dataset. So this is quite good performance for this task, and I should say that nice job you did. And in the next tutorial, we'll learn how to obtain even higher accuracy by systematically searching for better hyperparameters. So I mean learning rate, layer dimensions, number of iterations, and others. So this was quite a long tutorial. Now, when we know how to build a deep neural networks, we can learn how to optimize it. So I'll show this in my next tutorial. And of course, as I said, I should use this on cats versus dogs classification, but it takes a very long time. So to show you our results, I made this on this simple dataset and shown how it works in my real time, in real video recordings, not in the some background and whatever. So anyway, it also should be a little bit better, but as you can see, it takes a lot of times to train. So see you in the next tutorial, where I will show you how we can even more improve our model. So that's it for this tutorial. So I'll upload this tutorial code and cats versus dogs image dataset on my GitHub. You can visit it there and try it yourself. So thank you all for watching. I hope this tutorial was useful for you. Thank you all for watching. Good luck, and see you in our next video.